Hey, this is Bob. This is the McKinney Amateur Radio Club's general licensing class, a class in which we will cover the technical aspects of the exam for the general license. We're assuming that you can read the book basically and get the operating instruction questions down and the rules and regulations questions, et cetera, which are relatively straightforward. So as I said, this will be strictly dealing with some of the technicalities. We'll start with some slides that are of general interest, just covering some general topics, and then we'll start going into the individual sections as are given in the various guides. I'll be using the Gordon West materials. I like his materials, although his organization sometimes makes life a little bit interesting, but that's okay. We'll do that anyway. Also, we'll occasionally make reference to the ARRL materials, which are also very, very good, and you can, of course, use either one that you like. And then this will be, as we said, this is being recorded, and it'll be posted later on for you to review if you should want to do that. And right now, we're waiting for everybody to get here, and as soon as we get here, we'll get started. I hit the right. Okay, and we are now recording. I'm going to share my screen at that point and bring up the PowerPoints. That one, and share it. And go to, come on, be nice. Come on. There we go. Okay. Everybody see my screen okay?
Yep.
We're good? Okay. So I've already given you the little quick introduction there. This is just a little supplemental material to get started with, kind of laying some foundation. We'll talk about this a little bit as we go. My premise on doing the 1 hour sessions, by the way, is I'm guessing we'll spend about a minute to a minute and a half per question. And so that's kind of how this is timed. You'll see in another slide here how many slides are involved in the different things as we go along. So this is what we're going to try to do today with our intro section. We have 18 slides in that one. Electrical Principles has 61 total slides, of which we're actually going to do 27 plus a couple more that are good basic material as well. And then next session, hopefully oscillators, components, and so forth, as you can see down the way. And some of that we'll take with a grain of salt. If we get there, fine. If we don't, we'll pick up where we leave off on the next time around. And by the way, if you have a question as we go, just yell at me and say, hey, what about this? Okay, start with the metric system. We're full of that. As you probably know, we have K ohms and megohms and millihenries and microfarads and all those different things that we deal with. So you need to be a little bit adept at moving the decimal point around just a little bit, especially with the minus or the smaller quantities, the millis, the thousandths, the micro, the millionths, the nanos, and the picofarads or pico, whatever it happens to be, usually picofarads. So just be aware sometimes you need to move those things back and forth, and don't let it scare you. It's really not that scary. Okay, Ohm's law. We need to have a little bit of Ohm's law in our background because that's the main thing that we use for figuring out what's going on in any given circuit. It lets us know about the voltage, the current, the resistance that are there, and how they interact. A certain amount of voltage will push a certain amount of current through a certain resistance, and we can calculate what those things are ahead of time and see if we're going to overpower or overdo some circuit, see if the circuit can handle what we've actually told it to do. So EMF is the old term electromotive force, which we represent by the letter E, which is voltage, but we still use the old EMF, the letter E. Current, we use the letter I for intensity, because essentially current is the intensity of the electrons flowing through a conductor of some kind. And then resistance, R, is whatever is impeding the flow of the current through the particular circuit. So E is in volts, I is in amperes, R is in ohms. The basic formula is E equals I times R. Now, if you pronounce that EIR as in ear, that's kind of a memory hook for you if you want to do that. One of the things I think that has served me well anyway, you may or may not want to do this. One of the things that has served me well in taking the test is I take in a clean sheet of paper, which you're entitled to do. I also take a calculator just in case I decide I want to use it, though I usually don't. But on that piece of paper, the first thing I do is I write down E equals I times R. And then notice the power formula at the bottom of this, P equals I times E, or pi. So I write down ear and pi. And then the derivatives of those formulas, E equals I times R, I equals E over R equals E over I. So I'll have those if I want to use them. Likewise, power is current times voltage. Current is power divided by voltage. Voltage is current divided by power. And if you need other things there, we can use those last two. Those are not used quite as much, generally speaking. And some of those answers, some of the math stuff, unless you really like to play with algebra, you can really just memorize the answer quite easily, and that may be an easier way for you to go. I would not say go one way or the other. Go with whatever works for you. Okay, basic sine wave makes everything happen in the AC world, the alternating current world. As you can see, we start off at a given point over here. The voltage rises to a certain point, to a peak, drops back down to the zero again, then descends down to the negative peak again and back to the starting point. That would be 1 cycle or 1 hertz. We measure the time it takes to go from there, from the beginning of it, to where it crosses the line over here again. That's 1 time period. They're representing it here as from 1 peak to the next peak. It doesn't matter which place, wherever you start, you stop at the same place to get 1 cycle. That's what they're after. And then we have a little formula for that. Frequency is equal 1 divided by the time. So if it takes 1 microsecond to go, back up. If it takes 1 microsecond to go from there to there, we can do 1 divided by 1 microsecond, which is 0.000001, which gives us 1 megahertz. So we can go back and forth with that if and when we need to do that. Then we measure the peak of the voltage as it goes to the positive side, showing voltage peak here. Likewise, we can do the negative peak if we wanted, or if we go all the way from the top to the bottom, that's called peak to peak, and we'll see some places where we'll be called on to give some information about that. Then the RMS voltage that's there is the equivalent that this particular voltage sine wave would give us if it were DC current instead, if like it were a battery, for example. So we'll see the RMS values applied to a number of places. RMS stands for root mean square. You don't necessarily need to remember that. It's just one of those crazy terms. And I'll show you some formulas for this in just a second. This is just another picture of it showing basically the same thing, with only 1 wave there. We have the peak value there, and of course the peak value at the bottom. Peak to peak all the way from here, all the way down to the bottom down here. The RMS value, that one that we talked about, is the equivalent to DC, is 0.707 times the peak value. You will use that one. Average you will rarely use. Average is literally just what it says. It's averaging out all these values all the way across the waveform. We rarely use those, but it's a formula that's there. You don't generally see that in most things. Now, the formula's at the bottom. The average, as I said, you probably are going don't even worry about that. But RMS is 0.707 times the peak. And notice that's just 1 peak. If it specifies peak to peak, then we have to multiply by 2. Does that make sense? So far, so good? Okay. And this is just a little chart that shows you the thing, how to solve for those things. If you want to take a screenshot of that, or if you have your camera handy and you want to take a snapshot of that, or if you want me to mail you this slide presentation, I'll be happy to do that as well. And then you'll have this handy if you want to use it. Okay. Capacitors, one of our main building blocks. A capacitor stores an electrostatic charge. It stores that charge on 2 metal plates separated by an insulator of some sort. The 2 metal plates oftentimes are aluminum foil, and the insulator in between can be paper, it can be wax paper, it can be any number of things, it can be mica, any number of different things for the insulator itself. When we put a voltage across a capacitor, we put an electrostatic charge on those 2 plates, which it retains for a period of time on its own. It's measured in farads. The farads came from Michael Faraday's name. Farad is a huge quantity. So rarely will you see anything actually specified as a farad. Normally you will see it start with microfarads or 1/1,000,000th of a farad. That's usually the starting place. And then we go into nanofarads and picofarads very often. That's not unusual at all to take it on down just a little bit further. Okay, we've got somebody else coming in. Just a moment, please. Okay, we're talking about capacitors. They store an electrostatic charge between two metal plates separated by an insulator. They're measured in farads, which is a large, large quantity. We usually start with micro or millionths of a farad when we talk about that. When we put a capacitor in an AC circuit, and the resistance to current flow through that capacitor is called capacitive reactance. Unlike current flowing through a resistor, which is constant no matter what, the current flowing through a capacitor will vary with the frequency. Hence, the capacitive reactance, or the amount of resistance that it submits to the AC signal, will vary as well. And that's called capacitive reactance, represented by X sub C. X is reactance, and C means that we're talking about the capacitance portion. And it's measured in ohms, just like resistance is. Likewise, okay, come on now. Likewise, and I'm losing my gadgets here. Likewise with inductors, there we go. Inductors are just coils of wire. Basically, they may be wound around an air core, meaning there's no metal core inside the coil of wire, or they may have some kind of a ferrite or metal, something inside the center as a core. At any rate, an inductor or a coil will store an electromagnetic field or charge, if you'd rather call it that. Essentially, we apply a voltage to it. It builds up a magnetic field, and then that magnetic field can sit there, and as long as DC is applied, it will just remain static. But in the case of AC, it will build up the field, the flow will reverse, and then the field will collapse upon itself. The inductance that is presented here is called inductive reactance, or X sub L. You remember, X means reactance, L meaning inductance. It's measured in henries, which again is a fairly large quantity. Usually you'll see inductance starting out in millihenries. You'll see some microhenries, but usually you'll see millihenries in most cases. And of course, it's measured in ohms as well. And we just mentioned transformers. Transformers are coils of wire, normally wound around iron cores of some kind, and they can still have reactance, of course. But with transformers, we generally don't look at them in terms of inductive reactance. Most cases, we're looking at them for the number of turns of wire that's wound around that particular iron core that we have there. Okay. Impedance. Reactance is the resistance to the flow of AC through a capacitor or an inductor. If we put a resistor in there with it and combine all three of those, then it's called impedance. It impedes the flow of AC, and it's represented by the letter Z. Total resistance to the AC current flow through a circuit is its impedance, or Z. Combines the resistance, the inductive reactance, and the capacitive reactance. They're all listed in ohms, so they add together. It will vary with the frequency again. And then we have another term to throw in there called resonance. Resonance is that spot at which the inductive reactance is equal to the capacitive reactance. And when that's the case, they cancel each other out. So if I had in series a 50 ohm resistor and an inductor that presented 50 ohms at its particular frequency, and a capacitor that presented 50 ohms reactance at that same frequency, the inductive and the capacitive reactances would cancel each other out, and the resistance to that current flow would be only the resistor, the 50 ohms. Now, the resonance is a very important thing. Resonance determines when a frequency can pass through a circuit. Oftentimes we use that in tuning many times, or in filtering. We'll set a resonant point in a circuit so that this particular frequency will just pass right on through unimpeded. Anything outside of that frequency will be rapidly deteriorated as it goes through. It'll be reduced as it goes through, and we'll see some more of that as we go. Are we okay so far? Okay. A couple other formulas that you'll see along the way. You may or may not want to use these. If you do, you can. Again, as I recommended in the beginning, if you have your sheet of clean paper, when you sit down there and you write out your EIR and the PIE formulas, you can write these two formulas down just so you have them in case you need them. Capacitive reactance for a capacitor is determined by 1 divided over 2 pi frequency capacitance. So 1 divided by 2 times pi times the frequency in hertz times the capacitance in farads. And so you have to watch those terms and make sure that they are in hertz and the things are in farads or portions that, i.e. microfarads, whatever. Likewise, inductive reactance is X sub L, or inductive reactance, equal to 2 pi times frequency times the inductance in henries of the inductor itself. And again, as I said, if you want this particular little slide thing, if you'll email me, I'll be more than happy to send it to you. Okay, this is just a chart listing all those same things. Of course, this is a graphic. This is not text. My formulas were done with text. This is done with graphics, so you can see the 1-overs, which makes it a little bit easier to see. It's the same things that we were just talking about. Inductive reactance is 2 pi of L. Capacitive is 1 over 2 pi of C, etc. Another way to look at it. Ohm's law in AC circuits. We talked about in the beginning Ohm's law for DC circuits, where we said the E, or E equals I times R. Voltage is equal to current times resistance. This is important to calculate impedance then in an AC circuit. It works exactly the same way as the DC. The terminology is just slightly different. We still use E for voltage, or electromagnetic force. We still use the letter I for current to represent the intensity of the current flowing. And then the impedance represented by the letter Z. You remember, impedance is the composite value of the resistance, inductive reactance, and capacitive reactance all summed together. Impedance is listed in ohms, just like resistance is. So the formulas for that: voltage is equal to current times impedance. If it were DC, it would be current times resistance. It's working exactly the same way as it works with DC circuits. And so forth. And power is the same way. Power is current times voltage. Power is in watts. And then we get out to the resistance portion, we use Z instead of R. That's really all it boils down to. And of course, the way we derive these formulas, by the way, these little guys down in here, that's just some basic algebra to do some substitution so that we can derive those formulas. If you're good at algebra, you can play with those if you like, but it's not really necessary to do that. And then we have the little wheel, as we call it, the impedance wheel or resistance wheel. Again, the EIR, which we pronounce as E, or E equals I times R. And then PIE, power is equal to current times voltage. And then all the derivatives of that are listed in that circle. That's just for your information. If we're doing AC circuits, as it says there, we replace the R with the letter Z. It works exactly the same way. A couple other things that we'll see along the way are time constants. Time constants, that's the time it takes a capacitor to charge up to 63.2% of the applied voltage. Once the charge on the capacitor reaches 63.2, the capacitor is considered to be charged. It can go higher than that, but that's considered charged. Likewise, if we put a resistor across that capacitor to discharge it, when it falls to 36.8% of that voltage that was applied, is considered discharged. Why would we care? because the time constant is something that we use to determine frequencies that a filter will respond to. We can design a filter easily with a certain time constant so it will filter out or it will enhance or take away from something that's passing through it. So it's important. So time constants. Now, we have a little more on time constants. Okay, we can do either a capacitor or an inductor, of course, as we said, and we have the resistor there to make it charge the inductor or discharge the inductor. The time constant is equal to the inductance divided by the resistance of the inductor. And again, we're at that 63.2% to be fully charged, 36.8 to be discharged. Works the same as the capacitor as far as those are concerned. Now, I'm getting a dry mouth. Excuse me. As we look at all those different things going back and forth, AC circuits present their own unique situations when we deal with the current flow through those and frequencies and all that. So somebody came up with this wonderful little way of remembering some of these things that cause these inductances to change, which we call Eli the Iceman. And the reason for that is, now I'm going to go forward and I'm going to come back to this slide. I'm going to go forward just a second. When AC passes through a circuit, if it's passing through an inductive circuit on the left, you notice that ELI means voltage leads current. In that particular case, Eli, and it's an inductive circuit. In that case, the voltage goes high before the current gets there. And that's just, it goes into a lag because it's charging up that inductor. It takes a little bit to bring that charge up on the inductor. Conversely, on a capacitor, which is the other half of that slide, the current charges up first, and then the voltage follows as the capacitor charges. So we use this little thing, Eli, the Iceman, as a memory tool, basically, to remember how to look at those things. Voltage leads current in an inductive circuit. Current leads voltage in a capacitive circuit. And you will see that on the test. Okay. The J operator, it's not something that's dealt with, but it is mentioned, and it's just nice to know as well. The J operator, the J is defined as the square root of -1, which is an imaginary number. There's no such thing. But it's used to represent some different values. And for our purposes here, when we see the J operator used with a resistance, it'll be usually with a plus J or a minus J, like minus J25 or plus J36 or something like that. Usually you would see that when you're measuring an antenna's impedance. And your meter, if it has that capability, like many of the old MFJ meters would actually give you this, they would say that your resistance on your impedance on your antenna is 50 minus J25. The minus meaning it's inductive. So you have 50 ohms of resistance and 25 ohms of inductive reactance, which means you need to add some capacitance or decrease the inductance in order to reduce it down to zero. Ideally, the antenna would be 50 plus J0. In other words, no reactance at all there in that case. So minus J25 would be the 25 ohms capacitive, plus 25 would be 25 ohms inductive. And it's important because we do see that happen sometimes. When we get the 50 plus J0, meaning there is no reactance there that's taking place, and we're just seeing 50 ohms resistance, the maximum power transfer then can occur from our radio through the feed line to the antenna. That means that the antenna is resonant. Here again, capacitive reactance equals inductive reactance, which means you have an exact one-to-one match between your coax line, your transmitter, and your antenna. Now, from a practical standpoint, small mismatches, 3-to-1 or thereabouts, generally can be compensated using a tuner if you want to do that, and you'll be just fine. Many radios have built-in tuners. Most of those will handle a 3-to-1 SWR and will take care of that. So SWR is that ratio of how badly mismatched we really are. If we're 1-to-1, we have a perfect match. 3-to-1, we're not matching as well as we'd like to. It doesn't get terribly serious until you get up a lot higher than 3-to-1, however. And again, some antenna analyzers actually show you that J operator, and you can use that to know if it's capacitive or inductive if you'd like to know that. And it does mention the J operator on the test. One other little thing about antenna formula. On the test, they're going to use that middle formula. Half-wave antenna length in feet is equal to 492 divided by frequency in megahertz. And that will give you a value in feet for a half wave or a dipole antenna. Where does that 492 come from? And I've got a slide that follows that we'll talk just briefly about that. It's not on the test. Just want you to be aware of it. The 492 does not take into account the velocity factor of a feed line. When a signal goes through a feed line, coax, whatever it is retarded just a little bit. It's slowed down just a tiny bit. So most places we use a velocity factor of 0.95. So this one megahertz going through there will be slowed by 0.95. And because of that, it changes the length of the antenna. That's the idea behind that. The 492 is what's used on the test. They don't deal with the 0.95 velocity factor. But in real life, and by the way, these the other numbers that are on the screen, where you see that, the half wave, the 492, half of 492 is 246. 2 times 492 is 984. So that's where all those come from. Now, with the velocity factor, a half wave is 468. Now, this is real life. This is what, if you're going to measure an antenna, you want a 20-meter antenna, which is 14, say the middle of the 20-meter band, 14.15. So we would use the 14.15. We'd divide 468 by 14.15 to get the actual length of a half wave antenna, which is about 32 feet. And that'll be very accurate. Where the other one, it won't be quite as accurate. It'll be a little bit longer. Now, that's not all bad, because if it's too long, you can always trim it off. If it's too short, it's another issue to add length onto an antenna wire once you've already cut it. And this is how that's all derived, if you're interested. The length of the wavelength is 300 million meters per second divided by the frequency in hertz. And then we divide, as you can, if you want to go down through that, you can see all that stuff that we come up with. And then we say the speed of RF in a wire is about 5% slower than in a vacuum, in a theoretical vacuum. And we put that factor in there, and we come up with that 468. That probably doesn't really matter, to be honest with you. It's just gee whiz. Again, you're welcome to this little slide pack if you want it. Okay, that takes care of that one. I'm going to stop the share for a moment, and then I'm going to go and share a different one. Any questions while I'm bringing this next one up? Let's see, is that the one? Electrical principle. Yep, that's the one. Okay, and we're going to go to that one, and we're going to tell it to go screen. Okay, this is the little introductory thing that Gordon West has done in conjunction with the W5YI group with whom he works. And as I said, this is made available to us who are registered instructors with them. You might remember that this particular license manual is good through June 30th, 2027, at which time the questions will be shuffled and revised and added or changed or whatever. And they do change the questions, by the way. To study for the question or the exam right now, you would be in trouble if you used a license manual that was 10 years old, because a lot of the things that they're asking today, they didn't ask 10 years ago. Believe me, I know. This was kind of a wake-up call for me. Okay, electrical principles. I'm not going to dwell on this, but you'll see these are the same things that I talked about originally. E equal the square root of power times resistance. Those are just the formulas we talked about. So I'm going to go through these real quickly. I want to get down to slide number 10. Okay, we've seen this before, but just one more time for a quick review. The root mean square RMS value is the effective value. It's the same as the DC voltage if you were using a DC voltage for it, 0.707 times the peak. Just remember that if they want peak to peak, then you have to double it because it's based on the peak value itself. Okay, to convert from RMS to peak, we have the formulas that are there, and I'll show you those formulas when that actual question comes up. That's by the way, this thing over here on the left, this G5B08, is actually the question number, especially if you're using, oh boy, I thought I brought my manual in here. I didn't. If you're using the ARRL questions manual, they have two manuals. They have the big one and then the small one. The smaller one is actually arranged by question number, so it makes it really easy to look one of these things up if you need to look it up and get more information. So that's what that number is about. And as I said, when we see the question, we'll work this same formula one more time. Okay, I want to do next one. Same thing here. You're asking for a root mean square value. They're just showing the formula we're going to use. The answer to that question is going to be 12 volts. And I bet you'll remember 12 as soon as you see the question. And then this is one that's just kind of an interesting tidbit that we need to remember. Most of our power supplies today are switching power supplies. That's as opposed to a linear power supply. The old linear power supply were huge and very heavy and quite expensive because they used a huge transformer inside the power supply. They would use a big transformer to step down the 110 volts AC going into it down to somewhere around 12 volts. And then we would go through a rectifying process to convert the AC to 12 volts DC. Then we would have to do some serious filtering for it in order to make it work. All that making it very heavy, very big, and very expensive. The high frequency switching power supplies, however, let us use a lot smaller components, a lot lighter weight components. And of course, it keeps the costs down because you don't have that huge transformer that you have to deal with. Okay, and then from there, I'm going to jump on up to here. Talking about rectifiers there. Yes, go ahead.
I had a question, more of a statement. I was told that the linear power supplies don't put out as much RF noise or quiet.
Yes, the linear power supplies are great in that they don't generate RF. The switching power supplies, because they're using a high frequency oscillator to generate or to convert the AC down to DC where we want it. They do use high frequency oscillators, and those do have interference. They do generate RF interference. Many of the switching power supplies have a tuning knob on them. So if you're getting a noise at a particular frequency, you can move that little knob and move that particular birdie, as it's called, to someplace else so you don't hear it. Good point.
Mine does not.
I'm sorry.
I don't have one of those, but I just wanted to check and confirm that because switching are so much cheaper.
Yeah, exactly. It can be made with lighter, smaller components, and they're a lot cheaper in the long haul than the big transformers. That's basically what it boils down to. Going back to the power supplies, a half-wave rectifier uses only one half of the AC cycle, so it's wasting one half. Basically, it's very inefficient. When we look at the AC cycle as it goes through here, when it goes all the way from the top peak to the bottom peak and back to the center, that's considered 360 degrees. So we're only using 180 degrees of the sine wave, the top half, in most cases. Well, it depends on which way you turn the diode, is which half you use. Not that it matters. But the key is it only goes through 180 degrees of the input signal, and it only uses one diode for a half-wave rectifier. The problem with this thing then is we get these little bump spikes like this. We're basically just replicating this, going zip, 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 with a blank in between. Now we've got to do some serious filtering to fill in between those peaks. If we don't have good filtering and we put this on a radio, which is what we usually do, we would get a lot of AC hum, a lot of zzz, buzz in the background because of it. It wouldn't work well at all. So this type of power supply is very inefficient. It takes a lot of filtering, but if you're not requiring very much current, it's a cheap way to have a power supply. Conversely, we mentioned the 360 degrees that goes through that. This is looking at a different type of full-wave bridge rectifier. Full-wave bridge, meaning those 4 diodes you see down there in the middle of that little diagram. Okay. And with that, if you notice the output waveform, it shows the peaks now have been filled in a lot because we're not dropping that half cycle every time. We got all the cycles filled in. So we don't have to filter nearly as much. So we put our filter, this particular one is showing a choke and 2 capacitors, which makes it good. And then they put a bleeder resistor on the output. And there is a question about the bleeder resistor, by the way. It asks, why is it there? The bleeder resistor is there for the sole purpose of discharging those 2 capacitors. That way, if you open it up or you do something else, there's not a residual charge sitting there that could cause some damage to something else. Okay, let's see. I think those were the things I needed to do with that. Now, I'm going to fast forward here, so to kind of blink away for just a minute as I go through. We're going to go down to the questions, and we're actually going to start going through the questions. Here we go. Okay. What's the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? Okay, we're back to our power formula again. E is equal to the square root of the 1200 watts times the 50 watts. And if you multiply that out, it's actually like 2.49 and some change, closest to 245. And for most of us, we just look at that and say, okay, we're going to remember 245 volts rather than remembering the formula. But if you need to, you can. I didn't do the algebra here to convert this so I can pull the E out of that. That's why the square root is there. If you're good at algebra, you can do the conversions back and forth. I didn't do those. By the way, again, if I say something that doesn't make sense or I say it too quickly, please stop me and we'll be more than happy to talk about it. Okay, I think we're doing pretty good on time. And of course, in West material, when we click it the second time, we get the answer highlighted so we know for sure we got it right. Okay. How many watts of electrical power used if 400 DC is supplied to an 800 ohm load? Again, just using Ohm's law and the power formulas again, and we come up with 200 watts. And that is the correct answer. Again, if you're like me anyway, when you see this question again, 200 watts will just pop out to you. I mean, it's pretty obvious that that's what it is. You don't actually have to compute it. Same thing with this one. How many watts of electrical power used with a 12-volt light bulb drawing 0.2 of an amp? That's a simple one. P equals I times E. I is 0.2. Voltage is 12, which is 2.4 watts, just as it shows. How many watts are consumed with 7 milliamps flows through 1.25 K ohms of resistance? This is where our metrics come into play. 7 milliamps is how many amperes? We've got to move the decimal point now. Milli means thousands, so that's 7 thousandths of an amp, or 0.007 amps. Our formulas are working with amperes. So we have 0.007 squared times the 1250 ohms. Now, 1.25 K ohms is 1250 ohms. There we're moving the decimal place 3 places to the right. So K ohms, thousands of ohms, 1250 ohms. Multiplied gives us 0.06125 watts, but they're not giving the answer in watts that match that. They're looking for milliwatts. So again, we move the decimal place in our answer, the 0.06125 watts, move it 3 places to the right, and we get 61.25 milliwatts, or thousandths of a watt. They're playing games with us here, but to see if you're paying attention to the metrics. That's really all they're doing with that. Okay? Are we okay with that? Okay. And again, approximately, if you actually do these on a calculator, they don't always come out the exact answer, but it will be close. It'll be close enough that you couldn't pick the wrong answer. PEP is another term that we use. Peak is peak envelope power. Usually that's used with RF, but it doesn't necessarily have to be. But anyway, what is the peak envelope power produced? 200 volts peak to peak across a 50 ohm dummy load here. So they're basically talking about the output of a transmitter, the PEP output, giving 200 volts peak to peak across a 50 ohm dummy load where you're checking your transmitter. Okay, the formulas for that are given at the bottom. So 100 times 0.707, and then that squared and divided by 50 comes out to be 100 watts. Like so. And again, probably just remember that and you're okay. If you want to work it, though, it's okay. I mean, there's nothing wrong with working. Again, if you want to do those things, it's wise on your clean sheet of paper, write those formulas down before you ever get to it. And then you'll have it when you're ready for it. Value of an AC signal producing the same power dissipation in a resistor as a DC voltage of the same value is called what? Okay, you remember what is that thing called that's the equivalent to a DC voltage in the AC world? Starts with an R. Root mean square? Would you buy that? Okay. That's the equivalent. Basically, what they really define that is that's the amount of heating result that you would get with that much DC. That's where you would get the same result with AC, with an AC with an RMS value of that. Okay, peak to peak. Watch out for that because we got to multiply times 2. Most of our formulas are in peak, not peak to peak. What's the peak to peak voltage? Of a sine wave with an RMS voltage of 120. So here again, we're playing with the formulas. The voltage peak to peak is the RMS value times 1.414. That gives you on peak, so we got to multiply it by 2, like we said, comes out to 339.4 volts, which is the actual answer on the test, by the way. What's the RMS voltage of a sine wave with a value of 17 volts peak? Again, we're playing with the values. The peak voltage times 0.707 gives us 12 volts. 0.707 times 17. Which of the following is characteristic of a switch mode power supply compared to a linear power supply? This is what we talked about earlier. What do you think? Can somebody give me an answer?
C.
I'm sorry, did you say
C?
C as in Charlie?
Yes.
Exactly. Exactly. The higher frequency of the switching power supply lets us use lighter, smaller, less expensive components. Fewer components is definitely not the answer because there's 20 times more components in a switching power supply than in an analog supply. And then faster switching times doesn't really have anything to do with it. And it's not inherently more stable because you got a lot more electronics in there that all have to work together to make it stable. So the C is by far the correct answer. What's the characteristic of a half-wave rectifier and a power supply? And we mentioned this one. Anybody remember? Do you remember one of the old thumbnail principles on tests? Oftentimes the answer will be either the shortest answer or the longest answer. So what do we think is right here? Well, one diode, that's the circuit, by the way, at the bottom. I pasted that in there. This wasn't in the original slides, but I thought it would be helpful to put that in there. Only one diode is used there, that's for sure. The ripple frequency is twice that. No, actually, it's half of it. More current can be drawn? No, because we're only using half the wave, so we're not going to get more current out of it. The output voltage is 2 times the peak. No, we don't have anything to multiply it. So really, there's only one answer left, and that would be A. It only takes one diode. What portion of the AC cycle is converted to DC by a half-wave rectifier? The one there that we just looked at. Okay, 180 degrees. It only takes half of the wave. A full wave is 360 degrees. A half wave is 180 degrees. What portion of the AC cycle is converted to DC by a full wave? Now we're using both halves of the sine wave, and so we're going to use all 360 degrees of it. 180 on each side, 180 on the positive peak, 180 on the negative peak, 360 degrees total, which means it's more efficient and it's easier to filter. What type of rectifier circuit uses two diodes and a center tapped transformer? Do you remember that diagram that we looked at first that had 4 diodes in it? That's called a full wave bridge. A center tap transformer doesn't go into a full wave bridge. A center tap transformer goes into 2 diodes, as this is showed here. So what do we got there? Synchronous means nothing. Full wave bridge is wrong. And half wave doesn't work because there's 2 diodes, so that only leaves one answer, full wave. So each diode is taking one half of that sine wave and putting it to the output. So we get both halves of the sine wave in use. The downside to this is the transformer. The transformer, of course, is going to make it a little more expensive. Plus, the output of the transformer from end to end has to be twice the voltage that we're looking for, because we're only using from one side of the transformer to the center tap in the middle of it, or from the bottom side of the transformer to the center tap in the middle of it on either half cycle. So the full wave bridge is a good way to do it if you're using a transformer. If you needed line isolation, for example, from the AC line input, this is a good way to get a good safe power into a circuit someplace that you want isolated from the line. What is the output waveform of an unfiltered full wave rectifier connected to a resistive load? So we got a full wave rectifier, which means we're using both halves of both peaks of the sine wave, but we've got no filters on it. So we're just going to see those little blip, 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 blip things going through. A series of DC pulses at twice the frequency of the AC. DC pulse is the same frequency as the AC. A sine wave at half the frequency, or a steady DC voltage. Well, we know it's not going to be a steady DC voltage because there's no filtering. So what do we think? How about we go with A? At twice the frequency of the AC input, because each piece of each peak, positive and negative, is counted as one of those pulses. So if we had had a 60 cycle in, then we would have a 120 cycle ripple, be twice. Which of the following components used in a power supply filter network? Now, filter, we're talking about those components that were past the diodes and all those things that were making the conversion from AC to DC. Now we want to filter that pulsating DC that came out. So we're not going to use diodes. That was used to create this pulsating DC. The transformers could be used to transform a voltage from one to the other. There's no such thing as a transducer in this case. Capacitors and inductors, we're going to use both of those. Remember, we looked at that full wave rectifier, and it had 2 capacitors with an inductor in the middle and then a bleeder resistor. So capacitors and inductors definitely. Since diodes cannot be correct, B cannot be correct, D cannot be correct, then by process elimination, that leaves us with C. Which of the following is a characteristic of an electrolytic capacitor? The electrolytic is a special type of capacitor that gives us a lot of capacity in a small place. And the way they do that generally is by using foil plates. We talked about a capacitor is two metal plates separated by an insulator. So an electrolytic capacitor is usually aluminum foil for the plates, separated by a wax paper type insulator between them. The great part about that is you can roll that into a coil. So in a little sector this big, you can have several feet of aluminum foil rolled together and attached to each of the 2 plates, and you get a lot of capacity for a very small volume inside that little can. So I just gave away the answer, didn't I? High capacitance for a given volume. What's the characteristic of a? Whoa, wait a minute. What did I just do? Capacitors and inductors. We just said that, didn't we? Oh, I forgot to press the button. I'm sorry. Well, the function of a power supply bleeder resistor. Remember we talked about that? We had the filters there, and then the bleeder resistor. That sole purpose, that bleeder resistor was to do what to the capacitors? To discharge them, right? Okay. In most cases, you're not going to have a shock hazard out of a power supply like that. It's going to be 12 volts or something like that. You're not going to have a shock hazard, but you could have a burn hazard if you shorted that out or something like that, or you could get a surprise that you didn't anticipate. Excuse me. A digital multimeter compared to an analog meter. When you read an analog meter, you have to do quite a bit of interpolation. You have a scale that runs across and a needle going across that scale. And if the needle lands between 5 and 10, you look at that and say, okay, is that nearer to 10? Is it more like 7? Or is it nearer the 5? Is it really 5 or 6 or 7? So there's a lot of interpretation. With a digital meter, it's going to say 5.67, for example. So the precision is going to be much, much better when you use a digital multimeter. Makes sense? Conversely, when would you want to use an analog multimeter, though, instead of a digital one? Now, this question is a little bit hokey in one sense. Most newer digital meters have an analog reading on their meter. So you can actually see a voltage move back and forth. But before that time, you only had the voltage. And if the voltage were varying back and forth or moving up or down, you couldn't track it with the digital meter. The digital meter wasn't fast enough. So we used the analog meter, and that needle would actually move in consonance with whatever that voltage was doing. So if we're adjusting a circuit from minimum voltage, maximum voltage, somewhere in between there, we're going to set exactly on a particular voltage, then we could use that analog meter, and we can see exactly where it was at any given time. So it lets us adjust a circuit for minimum or maximum. One of the advantages to that one. Why do voltmeters have high input impedance? Most voltmeters will have an input impedance of at least 1 megohms. Most digital meters will have 10 megohms. Why do they need that really high input impedance or resistance for the meter? If it had a very low input impedance and you put the two probes that you're going to say you want to measure a voltage across a resistor, and it's got a low impedance, and you put the probes across the resistor, it's going to basically short out the resistor, and you'd not get a good reading. By using a very high impedance or high resistance, you put it across the resistor, it doesn't load the circuit down. It doesn't change the value of things flowing through the circuit, but the meter is geared such that it can still get an accurate reading by doing that. So what do we think? Doesn't have anything to do with frequency response. It doesn't allow higher voltage to be measured safely. High voltages are still high voltage. It doesn't help the resolution at all. So the only one left is decreases the loading on the circuits being measured. And this comes back to Ohm's law again. If you put two resistors in parallel, the ultimate value will be less than the smaller of the two. So if we have something, put something across a resistor that's low impedance, it will degrade the circuit and you'll get a very inaccurate reading. So we want to reduce the loading on the circuit under test. Advantage of batteries with internal resistance. Any battery has a certain amount of internal resistance inside it. The old carbon zinc batteries that we had, the old flashlight batteries, had a very high internal resistance. That's why if you loaded them kind of heavy, they would get hot quickly. And any battery, if you really load it heavily and you keep it there, it will warm up. And that's why it has an internal resistance. It's like a heating element inside the battery, basically. So an advantage of a battery with a low internal resistance is less heating, which means you can have more current flowing through it than otherwise. So the answer is it gives you a high current flowing through that from that battery, a high discharge current. Now, what batteries would have lower internal resistance? Almost all of our lithium-ion type batteries or LiPo batteries, lithium iron phosphates, etc. The nickel metal hydride batteries that we used to see were very popular have a relatively low internal resistance. Our alkaline batteries have a fairly high internal resistance. They're not very efficient in the long haul. So we want for our radios, we generally want those good batteries with low internal resistance so they can give us more current and not hurt the battery and continue to give us good service life. The maximum allowable discharge voltage to get maximum life out of a standard 12-volt lead acid battery. What's a 12-volt lead acid battery? That would generally be like the battery in your car. Those are generally 12-volt lead acid, meaning that the battery is made up of cells, and the cells contain lead plates inside them, submerged in sulfuric acid, hence lead acid. Each of the cells is 2 volts. And so we put 6 cells in a 12-volt battery to give us the 12 volts. So 6 times the 2 volts gives us 12 volts, correct? Now, what is considered the lowest discharge value you can have per cell? It's actually 1.75 volts per cell. So if we take that times 6, 6 times 1.75 comes out to be, guess what? 10.5. Now, you can remember all that, or you can just remember 10.5 if it's easier. Or if you forget, remember that each cell in a lead acid battery is 2 volts. 1.75 is the discharge stop point. Then you can calculate that out if you'd like to calculate it instead. It's up to you. Excuse me. Approximate open circuit voltage for a fully illuminated silicone voltaic, can't say photovoltaic cell, for goodness sake. What is a silicone photovoltaic cell? Solar panel, right? Simple solar panel. A single cell that makes up all the cells in a solar panel to give us whatever it is it's supposed to do. A single cell is a half a volt, as we see there. So one little cell, if we looked at a big old solar panel, pull one little cell out of it, it measures, it would be a half volt by itself. What configuration then of those individual half volt cells in the solar panel do we connect together? How do we get better voltage? Because half a volt's not going to help us a lot. So we're going to have to put a bunch of those in series to get 12 volts even. And one cell is not going to provide much current. So we're going to need to put them in parallel at the same time in order to boost the current and the voltage, which is why the solar panels are so big if they have a lot of capacity, because you have a lot of them in series and then those are in parallel. The series gives us the voltage, the parallel gives us the current. I think I gave away the answer, didn't I? Series parallel. Why should a series diode be connected between the solar panel and the storage battery that's being charged by the panel? So we have our solar panel set up. We put the positive input through a diode to pass the current into the battery, but the diode is there so that the battery will not flow backward into the solar cell. If we don't do that, and when the light goes out, the cell then becomes a drain on the battery, and it will actually discharge the battery over time. So we put that in there to do. This is one of those cases where the longest answer works. Prevent discharge of the battery through the panel during times of no or low illumination. No light, in other words. How are we doing? We're going to be a couple minutes over, but not much. What precautions would be taken connecting a solar panel to a lithium ion? They tell a little typo there. A lithium ion phosphate battery. Anytime you're using lithium ion batteries with any amount of capacity at all, you have to have a charge controller to go with it. The charge controller takes the voltage and the current coming from the solar panel and regulates it down to whatever it needs to be. Because if the voltage of the panel is not regulated, it can go up maybe 25 volts. We don't want that going to our battery. We want that to be regulated. Likewise, we want the current to be limited. So we need a charge controller to handle that for us. So the answer is D. We need a charge controller. Which of the following direct fused connection would be best for a 100-watt HF mobile radio? So we're going to put our radio in our vehicle. It has a 100-watt output. We run the wires from the radio through the firewall somehow up to the battery. We put fuses in the wires, and we hook the wires directly to the battery. The question is asking, what kind of wire would you want to use for that? Well, first of all, B, we're not going to hook it to the alternator or the generator. We're going to hook it directly to the battery. To the battery using insulated heavy-duty balanced transmission line. Transmission line doesn't carry that kind of current. We never use transmission line to carry power. And or to the alternator using the same thing. So the remaining one that's left there is we use a heavy gauge wire straight to the battery through the fuses. Why should DC power from a 100-watt HF transceiver not be from a vehicle's auxiliary power socket? They're talking about the cigarette lighter socket here, basically. When we put that 100-watt radio online and we turn it to 100 watts power out, most of those are going to draw between 20 and 22 amperes of current. Normally, cigarette lighter outputs are limited to 5 amps. So we have overloaded that cigarette lighter output tremendously. One of two things will happen. Either a circuit breaker or a fuse will blow, or the wiring that comes up to that outlet will melt. Neither of which is a good thing. So we never want to power a high-power radio off of a cigarette lighter. Likewise, if you go into the fuse panel on a vehicle, the same thing applies. You want to find a place on the fuse panel that has high output current to tap into to supply your radio if you're going to come off that way. But the main thing is you don't want to put this on the cigarette lighter because it can either burn up the wire on the cigarette lighter, cause a fire, obviously, or it can trip a breaker or blow a fuse. So the socket's wiring may be inadequate for the current being drawn by the transceiver. And it's going to make the wiring melt or blow the fuse. And we're there. Okay, it is hello time 8:03. We didn't do bad. That's not bad at all. I'm going to stop the share and go back to the screen. Okay. How we doing, gang?
I do have a question.
Go ahead.
It's it's unrelated to the test, but it made me wonder. You said the charge controller does it prevent overcharging so you could keep your battery hooked up to a solar charge controller and then not worry about it?
Exactly.
Okay.
Yes,
Perfect. I had that
that's
thought
correct.
today.
By the same token, you could leave the solar panel connected continuously to the battery through the charge controller. At night, it won't hurt anything. When the sunlight comes back up, it'll automatically kick in. The charge controller will take care of it, and it'll protect both the panel and the battery.
That's perfect.
Mhm.
That's perfect. Thank you.
Yeah, no problem. And by the way, the charge controllers are matched to the kind of battery that you have, because lead acid batteries charge at one rate, lithium ion charge at a different rate. So you need to make sure your solar controller matches the battery, or if it's an automatic one that will detect the battery type, and there are those out there that you can get, then you're okay either way. It won't matter, but it has to match.
That's great. Thank you.
Good question. Anybody else? You're going to be plumb easy on me, huh? Okay. Do you need my email address? Okay, let me go backward here. And there you are. You can use either one of those. The K5CRX at ARL.net doesn't always work, by the way, so watch out for that one.
We can't see it.
Can you see? Oh, we're not sharing. Doggone it. Just a second. Just a minute. I got to go back to. Why is it not letting me share? Share. Oh, that's why. Share. Sorry. operator error. There we go. Bob at rdcons.com, which is my own domain, or bdvance at gmail, or k5crxdarrl.net. I have not tested that one. It's supposed to be working, and I went in and checked it yesterday and told them to turn it on. So anyway, if you want any of these things, by all means, send me an email. I also have a terms paper that I did. It's about a 2 or 3 page document with a lot of the different terms about different things that we use in electronics and radio, of course. Be glad to send that to you as well. Anything I've got, you're certainly welcome to, is the bottom line. So any other questions or any other thoughts? Keep losing my mouse and all this. Okay, I'm going to stop the share with that one. Okay. Well, it's now, as I said, it's 8:07, so we've pretty well fulfilled our hour as we had intended to. This has been recorded. As soon as I finish here, I'll stop the recording, and then we'll see you next Thursday night, same bat channel, same bat time, and here we go again, and we'll pick up oscillators and components and circuits